Okay, folks, are you ready? Are you ready for these answers? Did you even do the problem yourself? Do you even have an answer in front of you to check? Chances are at least half of you probably don't, but that's okay. We're going to move on, whether you're ready or not. All right, so make the following compounds using any form of an acetylide ion and any other starting product. And we get 3 examples. And the first one is 1-pentyne 3-ol. Okay, so here's the problem. If you do not remember how to name a triple bond, you're going to be problematic. You are going to be struggling with these examples. And the reason is because they are assuming that you're an expert in every single thing that we've talked about already. So 1-pentyne 3-ol. Okay, so pent, 1, 2, 3, 4, 5. 1. Well, what does that 1 mean? That 1 means it's going to the ion, YN. What does YN stand for? Triple bond. There we go. All right, so that is what we need to see, 1-pentyne. And then 1, 2, 3 is the ol. So that is where my alcohol group is going to be located. All right, so the question wants to know, using at least acetylide or a form of acetylide. Okay, well, what does that even mean? All right, well, acetylide is C triple bond C at least with a negative charge and a hydrogen on one of them. But it also says any form of acetylide. So that means that this with not a hydrogen, but maybe some other random alkyl group could also work. They're giving me that choice. All right, so there's my molecule. I know that I have to at least use one of these versions, and it looks to me like one of those versions are right here, right? And it looks to me like this is probably what they used, because the C triple bond C is on there, on that carbon, and it's just carbon and a carbon. There's nothing else with it. So that's probably this C triple bond C right there. If there was something else with that carbon that made this longer, then I probably would want to use the second choice, because that random R group lets me pick whatever I want to pick. All right, so this is probably what they used. And, well, what kind of compound did they use to react with? Well, this OH is going to give you some insight in that. We know in all of these other examples that that C with the OH, that was the result of a carbonyl. That carbonyl bond was broken, that oxygen received a negative, and we protonated it to make sure that that is an OH and not an O negative. So basically what I'm trying to tell you is look for that OH group. And that OH group, what was it before? Well, you know that that was a carbon double bond O that was there before. And folks, those are the 2 components in order to make that product that you're seeing on the screen in the example. All right, so I'm going to take acetylide ion and I'm going to react it with an aldehyde here. And that aldehyde is a propanal. So propanal reacts with acetylide ion in a nucleophilic acyl addition reaction. So the acetylide ion is serving as the nucleophile that attacks the carbon of the carbonyl, that breaks the double bond, shoves the electrons up to the oxygen, and that forms a negative temporarily, and then we protonate it in the second round to make an OH group. So here, I need these 2 reactions, and in step number 2, I'll need an H plus in order for that to be completely satisfied. All right? And what's more, that H plus is probably not coming from a strong acid, so nothing like sulfuric, nothing like hydrochloric. It's coming from a very weak acid, so something like pyridine in order to get that to work. All right? Okay, so there we go. There you go, folks. That's what we're looking at. And we'll move on to the second example. All right, so the second example says 1-phenyl 3-butanol. All right, so it looks like they're giving me something a little bit more complicated. So 3-butan is kind of where I want to start. 1, 2, 3, and 4. And on carbon 3 of that 4-carbon chain, that is where my triple bond is going to be. So I'm going to number them 1 on the left, then 2, then 3. And then at my first carbon, it looks like that there is an OL there. That's what the name told me. So it's 1 all, and that's what that means. And then on the first carbon, there is also a phenyl group. All right, so there's 1, 2, 3, 4, 5, 6-membered ring, and a delocalized network that's directly attached, and that is called the phenyl group. All right, so this is what we have made, and we need to know what on earth have we done in order to make this reaction go forward. How can we make this? That's what they're basically telling me. All right, so let's just double check the nomenclature. Here is my first carbon, there is my second carbon, here is my third carbon, and there is my fourth carbon. All right, so there's 4 carbons, which is bute with a YN. It says 3 bute with a YN, so there is my third carbon with the triple bond. Then it says 1 all, so at my first carbon, there is an OH group, and then it says 1 phenyl. So at the first carbon, there is the phenyl group that is attached. So I need to know what on earth can I use to make this reaction go forward. And then it tells me that I could use acetylide in order to do this. All right, so C triple bond C with a negative at least has to be used. And that's pretty good because it looks like that's what I have here, a C triple bond C. And then this OH group, though, is a little bit further down than next door neighbor to the carbon triple bond. So you're probably saying, oh, well, we can use something like this then, right? Well, no, not necessarily. And the reason is because if this is what we used, this is the connector piece right here. This is what would go on to the main chain. And what we have here is a carbon triple bond carbon to the end. So if we add on an extra carbon here, it's not going to attach that way, folks. The negative is on the carbon of the triple bond. And if I'm thinking that this is the piece that was added on, well, this is not appropriate for that. All right, so the best that I can do is really to give you a negative with a carbon triple bond carbon. Right? I mean, that's really the best that I can do there. All right, well, if that's the case, then how on earth can I get this piece added onto the carbon? Because I know, just by looking at it here, in the very beginning, I know that here's my benzene ring. There's the carbon that has the OH group on it. And then we also have this other carbon that then has a C triple bond C on it. All right, well, if this is what you're thinking the nucleophile was, let's get rid of that. And that carbon is a very good sign, because it has an OH group, that is where the double bond was located. All right, so C double bond O with the benzene ring, which we call the phenyl, is a pretty good starting point here. The problem, though, is it's this group. This group that I am getting right there, how on earth can I get that onto the carbon? Because, once more, right now, the C triple bond C is not going to work out for us. Again, the reason is because the carbon involved in the triple bond is not attached there. In other words, this is what would be added on at that point. If you decided to add an extra carbon here, that's great, but this negative with the carbon, it's still going to add on to that carbonyl. That's where it's going to go. And this extra carbon is just going to come out here on the end. And that's not really what we're after here. That's not really what we want. So this one you might have struggled with a little bit. Out of the three, this one you're looking at and you're thinking, well, now, wait a minute here. Maybe that is the mistake that you did. Maybe you did go that route and you think, hey, I've got it. Here's my 3-carbon piece. I'll just put my 3-carbon piece on there and we'll go away and never have to worry about it again. This was easy. Okay, well, if that was the case, and that's what you did, you created a wrong answer because your triple bonded carbon would have attacked the carbon of the carbonyl. That is not what we want. We want this to be a little bit different because of that. So how do we do it? So folks, guess what? You can't actually make this product, not with what we have talked about up to this point. So if you wrote down that, well, you know, we can get close, we can kind of get this, but that is not really what they're after at all, well, there's no product that can be formed from this reaction. Now, we could make a product if this was a 2 instead of a 3. But because it's a 3, folks, there's no way that we can get to this major product that's right up here at the very top. And the reason is because of that carbon that is right there that's not going to work for us. All right? So if you chose to do this thinking that it would get you here, that's wrong. It's not going to work. And there's nothing that you can do at this point in order to get that product. All right, so the next one is 2-methyl-3-hexyne 2-ol. All right, so hex is 1, 2, 3, 4, 5, 6. And then at carbon number 3, we have a triple bond. And then at carbon number 2, we have an OH group. And at carbon number 2, we also have a methyl group. So this is the product that I'm after. And it tells me that I can start with acetylide or any form of acetylide that I want to. All right, so how on earth do we make the product? Well, if I take a look at this structure, I'm going to redraw this part of the structure first. And here is the OH group, and there is the rest of the piece that's there. Well, this is going to give me a very good indicator that this oxygen is probably at one point in time where my double bond was going to be located. Now, if the double bond is going to be there, I can't have that bond there, folks. It's got to go away because here's 2 from the double bond, and there's 1 to that carbon, and there's 1 down here to this CH3 group. So this is a ketone, and that's good news because the directions tell me start with an aldehyde or a ketone and plus any other reagents necessary, including acetylide or a version of acetylide. All right, so if that's my starting major molecule, there we go, that's a ketone. And this is actually, folks, CH3 on the left and CH3 on the right. Do you know the common name for that structure? If not, you better look it up. All right, so what can we add on to this molecule in order to get the product that we see up at the very top? Well, it looks like if we could add on that carbon with the triple bond C and the carbon, if we could add this on like that, then that is my nucleophile. That nucleophile will go into the carbon of the carbonyl, and it will the double bond, and that electron set will go up to the oxygen, and we eventually protonate that reaction in the very end. All right, so folks, that's how we make 2-methyl-3-hexyne 2-ol. And we do that by adding that organic with that version of acetylide in order for it to work. All right. Now, there could be an issue here. And the issue is, what if they just tell me acetylide and that is it? Okay, well, that's not a big deal. The other way that we make this is going back and taking a glance at what we did in the alkyne reactions. So in the first step, we added NH2, and that ripped the proton away, and that formed a carbon, triple bond carbon with a hydrogen, and 1 of those hydrogens have been removed at this point. If we need to elongate that piece, we do that by adding an alkyl bromide. So it looks like we need to add 2 more carbons here, right? So there's my 2 carbons, and here is the bromide point. So the bromide is the electronegative atom that pulls electrons away from that carbon, making that one partially positive, and this is a negative piece that is attracted to that partial positive carbon. So here we have a C, triple bond C, and then off of this is the carbon from the alkyl bromide and the remaining carbon from that alkyl bromide. Now that hydrogen is still there, but guess what, folks? I can put the amine in it again, and this will create that negative piece that I have here at the very end that we need. All right, so that was a review, once again, of Chemistry 251. So if you did not look at that in Chem 251, I'm really sorry. If you did have that for Chemistry 251 and you don't remember it, I'm sorry. So that's just the way that we make the acetylide piece. So if the directions state you can only use acetylide, then this is the step that we have to take in order to get what we actually need as a nucleophile in order to react onto that particular type of ketone right there. All right? Okay, so the next kind of set of reactions is something, again, that we have seen before, and this is called a hydride. Now, hydrides can react with carbonyls. They can react with type 1. They can react with type 2. We didn't really use them that much in type 1, but they can react with some of the type 1s. The mechanism is the same. We have a nucleophile that's going to attack the carbon of the carbonyl, and something is going to happen. A double bond's going to break. No leaving group is going to leave because there isn't a leaving group, and we're going to protonate the oxygen that goes there. But the hydride is basically a hydrogen with a negative, all right? So this is still a nucleophile. The nucleophile still behaves the same way in the mechanism. There is no difference. But the reason that we're introducing this is because you need to go back and remember how we form hydrides. This is not the first time that we've talked about hydrides, and we've talked about hydrides in Chemistry 251. And that was with something like NaBH4, which was sodium borohydride. So the sodium borohydride is used to generate the H-, and that H- will then at that point do what all of the other nucleophiles have done. It will attack the carbon of the carbonyl. These electrons get shoved up, and depending on if we have type 1 or type 2, we either have a leaving group that goes away, or that oxygen needs to be protonated after that point. All right, so that's the story with the hydrides. Again, nothing special, nothing that I have to kind of say, hey, you need to watch out for this. It's basically the same stuff all over. All right, so let me give you a real example here. Let's take a carbon double bond O with a hydrogen, and then over to the left, let's do a CH3, a CH2, and a CH2. And here we're going to react this in a two-step mechanism. In the first one, NaBH4, and in the second, a little bit of H3O plus or H plus. All right, so what kind of product is formed? Well, as with all of the reactions, I'll just like to redraw the starting reagents. So here we are. There's my double bond O and my H. So I kind of know now the NaBH4 is a hydrogen source, and that hydrogen source is a nucleophile, and that nucleophile is going to attack the carbonyl. So basically what that means is that this is going to, there we go. And when that happens, well, that allows room for that carbon to make an additional bond. This is an addition reaction because it's an aldehyde. It's a type 2. And that hydrogen from the sodium borohydride will be added to that spot. All right, so in step number 2, we have a proton source. And that proton source, of course, is going to help satisfy that oxygen that is negative at that point. So folks, this is just basically the generation of an alcohol. And again, at this point, I can pick up any alcohol reaction that I want to do with it. I will probably end up protonating the alcohol group in a form or a fashion, and I can get that OH group to leave, and I can make other things with that particular alcohol if I want. And the reason I do it is alcohols are very cheap, alcohols are very easy to obtain, and they're very easy to react with. So there we go. Once again, full circle all the way around. If I wanted you to go through and name what just happened, well, we can do that, right? We can get a name for this one. 1, 2, 3, 4. So this is a butane, the E, and add the Al for butanal. So butanal reacts with sodium borohydride and acid to produce 1, 2, 3, 4. So this is a butane, and add OL, butanol. All right, well, where is that butanol? Well, that's on carbon number 1. There we go. So our number closest to that functional group, and that just so happens to be the end carbon, and that would be carbon number 1. So butanol reacts with sodium borohydride and acid in a nucleophilic acyl addition reaction to produce 1-butanol as a product. All right, so see, there's nothing different here. It's just using a different nucleophile. That's all that we are doing and nothing more than that. All right, so let's do another example. CH3, CH2, CH2, carbon, double bond, and CH3. This time we're using a ketone just to allow me to prove a point, and that point is that ketones react the same as aldehydes do. All right, so here we have a ketone. We're going to react it with sodium borohydride and a little bit of acid all over again. So I'm going to redraw my starting reagent, and here it is. All right, and that is a hydrogen source for a nucleophile. So there it goes. And that opens up the site of attachment right there at the acyl carbon. That is going to take the hydrogen that I have used as a nucleophile from the sodium borohydride. And then this creates a O-. Well, step number 2 says I'm going to add a little bit of acid to it. So that will satisfy that O-, forming yet again another alcohol. All right. In the previous example, we had a primary alcohol. In this example, we have a secondary alcohol because that OH group is attached to a carbon that's attached to 2 others. So that is a secondary alcohol that we have formed. I can go through and name this just as before. We'll do a quick review. 1, 2, 3, 4, 5. So this is a pentane, add ONE, pentanone, and this happens at carbon number 2 because that's the way we get the lowest number. So 2-pentanone is going to react with sodium borohydride and a little bit of acid in a nucleophilic acyl addition reaction. And that acyl group is going to break the double bond, shove the electrons to the more electronegative oxygen in order to allow the nucleophile of hydride to attach to that carbon. That forms a O-, and that will become protonated, and we will end up making a 2-pentanol as a product. And again, it's a 2-pentanol because my longest carbon chain is 5, and we number closest to that end. So that will give me a 2-pentanol as an answer. All right. All right, folks, so there we go. There is something that maybe I want to show you here, and this is basically an example of a top 1 reaction. So we didn't really talk too much about this in top 1, but keep in mind top 1s have leaving groups. So NaBH4 and a little bit of H+ does the same thing here. This is the hydrogen generator, that's the nucleophile. This double bond O breaks initially. That adds on a hydrogen to that carbon. And then the oxygen, because this is a top 1, it's an acyl chloride, right? It's not a top 2. There's a leaving group here. So oxygen shoves those electrons back down in order to make a double bond, and then we get a leaving group that can happen because of this as well. And then we take a look at this and we'll probably say, well, that leaving group's going to go away because that's an ugly chloro, nobody wants it. And what we have here is a aldehyde, right? But if you take a look at this reaction scheme, look at what they're doing here. That's not really what we ended up with, was it? So in the beginning it is. Here's the hydride. It reacts with the carbon of the carbonyl. The electrons get shoved up. And then here the electrons get shoved down. and it reforms the double bond, and that makes the chloro group leave. So that's perfectly fine. So this is what we've ended up with here, right here. Look, it's an aldehyde. That's what you just told me. That's what we kind of did. But that's not what a product is. Why? The reason is because this is now an aldehyde. This is now a type 2 carbonyl that can react with the NABH4 again. So what we've done is that we've made a compound. That compound is perfectly legit. You were not wrong when you said that that is what was made. But we need to go another step further, and that's because aldehydes will also react with the nucleophile that is present. So the reaction doesn't stop. There's actually another chain reaction that begins to happen. So this aldehyde reacts as a type 2, and it will react with the hydride too, just like the acyl chloride did. So this is kind of the middle step here, because we're not yet done. So this type 2 carbonyl reacts with the hydride from the sodium borohydride that's there. There's nothing that we can do to stop it. It's going to happen. It's going to go forward. And here we get a carbon that double bond breaks to an oxygen. The hydrogen gets added on, but this time there is no leaving group. And then finally the H plus gets added on as well, and that H plus satisfies the oxygen, and that forms the alcohol. So in the beginning, if you did not know any better, you would have said that this reaction makes an aldehyde, and it does. But this is a middle step, because the aldehyde will then react with the hydride that we're using, because that's a carbonyl too, just like that's a carbonyl, and this reaction goes further, and it reacts one more time, and that still ends up making the alcohol that we have seen in some of the other examples. All right, so here's an example problem. Predict the products for the following if you react it with sodium borohydride. So 2-methylpropanol, cyclohexanone, and benzaldehyde. So those are the 3 examples that they want you to do. Take a stab at them, see what you come up with, react these 3 with sodium borohydride, predict your products, name everything if you can, and then come back in the next video and double check your answers. Did you get them correct? And if not, where did you mess up? So those are the 3 examples that we'll work on in the next video when you come back.